education activities at NASA to improving the visibility of mathematics amongst the various things that NASA does in terms of its education and public outreach. So without further ado, a little bit of a snapshot of the Parker Solar Probe. Of course, this is an artist rendition. There's no human there standing by to take a photograph with their smartphone of what the probe actually looks like. We love artists. They do a fantastic job these days, you know, getting the actual realism in check and making things look like you're actually there. It's a whole discipline in itself that's much needed in science. You know, people that have a capability of artistry and a flair for enjoying technology and natural phenomena, they definitely have a home at NASA to provide, you know, these wonderful imageries and movies, illustrated movies of a variety of phenomena. Anyway, the Parker Solar Probe was launched in 2018. Currently, it's in its 22nd orbit around the sun. And perihelion is going to be on roughly December 25th at a distance of about 7.3 million kilometers from the center of the sun. This is what the many orbits look like. It's a complicated orbit because actually it's harder to get close to the sun than you might think. You would think that all you have to do is let your hammer go at Earth's orbit and the thing will fall directly into the sun, but it won't. The satellites have to go through complicated orbits to lose enough energy to actually get close to the sun, and they have to do it in exactly the right way, timing-wise, that their perihelion arrives at the distance that you're intending it to and at the time that you want it to. So astrodynamics, as it's called, is an amazing topic and an amazing discipline. So anyway, why is the Parker Solar Probe doing all of this? Well, it turns out that the only way that we've been able to study the corona of the sun is by remote sensing. We don't have any way of actually going into the corona, and in a minute I'll explain why that's so difficult. So we really want to take measurements as close to the surface of the sun and within the corona as possible, so that we can learn more about not only the composition of the corona, but also the origin of certain things that are important to us here in the rest of the solar system. And amongst those is something called solar wind. This is an outpouring of matter from the corona, and it flows out through the interplanetary space. It was originally theoretically modeled back in the 1950s by Eugene Parker. And since then, we've been trying to understand the details of this solar wind, what energizes it, where the mass comes from that is flowing out, and a variety of other technical issues. So that's where we are, and Parker Solar Probe is dedicated to giving us a firsthand view of some of these phenomena close up, so that we no longer have to speculate about what things are, but we can actually put them in as observables in our theoretical models, and that's the goal. Here is what the closest approach looks like on an exact scale model of the sun and its corona. You see it gets pretty close. It gets to within about 4 or 5 radii of the, 6 or 7 radii of the surface of the sun. So it's right there in the inner corona region, and this is actually the outer limits to what we normally see during a total solar eclipse. So if you imagine the extended corona that you see during a total solar eclipse, well, the Parker Solar Probe is going to probe an area that's just outside that boundary. And that's where things get really exciting, because that is roughly where we think the solar wind gets a lot of its impetus. But getting this close to the sun, of course, is a problem. In fact, the space probe would heat up to about 2,600 degrees Fahrenheit if it didn't have a sun shield. And that sun shield looks very, very much like the ablation shields that are used on space shuttles and incoming spacecraft that land on the Earth after performing their missions. Very special material that has very, very low heat conductivity. So you can touch the backside of this thing, heat it up to 2,600 degrees Fahrenheit, and you would only feel that it's very gently warm. And that's really great because you have a lot of electronics back there that are very sensitive to heat. In fact, believe it or not, because of the particular circumstances of the way the spacecraft operates, you actually have to have heaters in some of these components because it gets so cold behind that heat shield in various parts of its orbit that you actually have to provide heat. The speed of the spacecraft is 400,000 miles per hour. That's an amazing speed. Things in orbit around the Earth only get up to maybe about 10,000 or 20,000 miles per hour. At this incredible speed of the Parker Solar Probe at perihelion, you could make it to Mars in 88 hours. Imagine that. You know, in nothing more than maybe about, well, less than a week, you'd be able to travel from the Earth to Mars if you could travel at the speed of the Parker Solar Probe. But of course, that's a very difficult thing for us to do. And we're expecting it's going to take for the first flights more like about 240 days to get to Mars. Okay, so Parker Solar Probe, discoveries so far. It's been doing this since 2018. It's been returning a lot of data, a lot of exciting discoveries. This is just a partial list of what's been going on. First, direct measurements and samples of the solar atmosphere, detection of the Alfvén surface where the solar wind originates, and so forth and so on. One of the exciting things for me, is that it used to be thought that coronal mass ejections were responsible for the intense solar proton radiation storms that we sometimes feel here at Earth. But it turns out, according to Parker Solar Probe's measurements, these solar proton storms are very common in the corona of the sun and within the mechanisms that operate there. And they're not all related to whether or not there's a coronal mass ejection in progress or not. So that was a rather dramatic discovery that has very striking implications for how we conduct space weather predictions at Earth. Okay, so what we're going to do is, here's problem number one. We measured the speed of the solar wind measured by Parker Solar Probe as about 350 kilometers per second. At that point where Parker was, the density of the solar wind was about 300 protons per cubic centimeter, and the distance was about 21.5 million kilometers from the center of the sun. What we'd like to do is figure out how much mass is represented by that speed and that density and at that distance being ejected by the sun every second. Because that'll tell us a number of things. It'll tell us, is the sun going through a phase where it's ejecting a lot of material such that the material lost will actually affect the evolution of the sun in a severe way? Or is it just a minor breeze that has really no physical or interesting significance to the evolution of the sun? So the way we break this up is the sun is a sphere. So we're going to use the surface area of a sphere is 4 pi r squared. But then to get a volume, we have to multiply that shell by a thickness. And what we're going to use as the thickness is the distance that the wind travels in 1 second, which is 350 kilometers. So this shell that we're going to erect around the sun has the radius of about 21.5 million kilometers, the surface area given by 4 pi r squared, and a thickness of 350 kilometers. We're going to calculate what that mass corresponds to, and that's going to be the mass ejected by the entire sun every second. So that's the logic behind this calculation. So, okay, let's go ahead and do it. The surface area of this shell is 4 pi r squared. And if you work out the numbers, well, you have to convert the million kilometers into million meters, and a kilometer is 1,000 meters. So you multiply the 21.5 million kilometers by 1,000, you square that, multiply by 4 pi, and you get 5.8 by 10 to the 21 square meters. That's the surface area of this sphere, this shell. The thickness, as I said, is 350 kilometers times 1 second, but then we convert that kilometers into meters by multiplying by 1,000, and so we get 350,000 meters. So if we multiply the area by the thickness to get the volume, we get about 2 by 10 to the 27 cubic meters as the volume of this shell. All right, that's step one. Now what we need to do is figure out what the density of the shell is, because we want to compute mass equals density times volume, which we use in a lot of different situations here on Earth for other things. The mass of the shell, as I say, is volume times density. What we know is that there are 300 protons per cubic centimeter at the distance of the shell. And so what we do is multiply the volume, which is 2 by 10 to the 27 cubic meters, by 300 protons per cubic centimeter. And then we have to do the conversion of cubic centimeters to cubic meters for the number of protons by multiplying by 10 to the 6. So in the end, we get 6 by 10 to the 35 protons as the number of protons in the shell. One proton has a mass of about 1.7 by 10 to the minus 27 kilograms. So multiplying the number of protons by the mass per proton, we get, in the end, we get about 1 billion kilograms of matter in this shell. So that represents 1 billion kilograms per second that the sun is losing in terms of mass. Okay, so that's the argument here. That's how we got to that 1 billion kilograms per second as the mass loss rate for the sun. And now we can compare that against other things that we know about the sun. For instance, one question is, at this rate, how much mass has the sun lost in its 4 billion years of being around as a star, as it is now? So we take that mass loss rate, which is 1 billion kilograms per second, and multiply by the number of seconds in 4 billion years. And if you go down the line, you find that that mass corresponds to 1.3 by 10 to the 26 kilograms. But the mass of the sun is 2 by 10 to the 30th kilograms. So essentially, the sun has lost 0.007% of its mass over the last 4 billion years from this solar wind effect. If we turn this into another number in terms of solar masses per year, we get about 1.6 by 10 to the minus 14 solar masses per year. And that's really interesting because the numbers that we've estimated in the past from other kinds of experiments that weren't in situ is a number between 1 and 5 by 10 to the minus 14 solar masses per year. So with this very simple calculation using Parker Solar Probe data, and this assumption of a shell of mass being emitted every second, we get a number that's completely in accord with what astronomers have deduced from other observations over the last few decades. Now, at this rate, there is no danger of the sun having any kinds of problems. I mean, this is an insignificant amount of mass compared to the total mass of the sun. And in fact, this mass loss rate never enters into calculations that are done for stellar evolution. Now, the caveat is there are some kinds of stars where this mass loss rate is 1 trillion times higher. So for those stars, this kind of a mass loss from a stellar wind can be a significant effect on the evolution of those stars. Fortunately, our sun is not one of those. Another thing that you might consider, and this is sort of intermediate level math because it involves some algebra, is how hot does the spacecraft get at its perihelion distance? Well, the relationship between the power output of the sun, the distance from the sun that you are, and the temperature that you get is given by this formula, which is a fundamental formula in astrophysics. For instance, if you know the radius of a star and its temperature from observations, you can determine what the luminosity of that star is. Similarly, if you knew what the luminosity of the star was from other kinds of observations and you knew its temperature, you could then deduce what the radius of that star was. And astronomers play back and forth with this equation and the observations they can do on distant stars to actually work up a detailed map of stars and their physical properties, spanning a wide range of luminosities, masses, temperatures, and radii. So if we use this fundamental equation, we can change the units a little bit so that they're more convenient for us. If we express R in millions of kilometers and L as the luminosity of the sun, this physical constant sigma is predetermined, then we get the interesting equation that T is equal to 4861 divided by the square root of the radius in millions of kilometers. And that will be a temperature in Kelvin units. And so if we plug in the distance of, well, the radius of the sun in these units, we get a temperature of 5850 Kelvin. And the actual number that people use from a more careful set of measurements is 5772. So we're definitely within a 5% ballpark of getting the right answer for the temperature of the sun. So one would hope that under different circumstances that apply to Parker, we could also get an estimate for its temperature as well. So we plug in 7.4, which is 7.4 million kilometers for the distance of Parker. We know what the luminosity of the sun is, and so the temperature equation gives us 1786 kelvins. And if you look at that number compared to the melting point of aluminum or titanium, it sits sort of right in the middle and actually closer to the melting point of titanium. So if the Parker Solar Probe were not shielded with a heat shield, it would definitely melt very quickly. And melting and essentially turning into vapor would not be such an inconceivable concept for the way that the Parker Solar Probe would end its life. But as I said, luckily it has a heat shield, which is dramatically effective. You can put 2000 Kelvin on the front surface near the sun, and 6 inches behind it, you're only at a temperature that's barely above room temperature on Earth. So it's a very effective heat shield. So now, an advanced question. We've gone a number of perihelion orbits shown in this table. 1, 4, 7, 6, 14, 11, and 10. Those are different orbits, different perihelia. The second column gives the distance that the Parker Solar Probe attained at each of these perihelion passes. And then on the third column, it gives the density of the solar wind, or the density of the corona, at each of these perihelion passes. So this is an interesting span of data. And what we would like to do, number one, from columns 2 and 3, we would like to plot density versus distance and come up with an equation that models how the density changes as a function of distance away from the sun. This is a fundamental equation that you are going to use, well, that astronomers use to test the accuracy of their theories, which will predict what this density profile should look like under various conditions. And those conditions, we hope, are constrained by data. So essentially what you have is a theoretical prediction of what this density profile looks like. And here, Parker is providing the actual data from in situ measurements. So if we do this kind of a modeling, well, first of all, let's use Excel spreadsheet and take the numbers in the table and actually plot them. And so we've got spacecraft distance in million kilometers on the horizontal, and we've got the proton density, protons per cubic centimeter, on the vertical axis. And we see that these numbers are not just scattershot all over the place, but they're actually correlated. And the correlation is that the farther away you get from the sun, the lower is the density of the protons that you find at that location. And that's an important 0th order prediction, that the farther away you get from the sun, the fainter the corona will be and the fewer particles there will be in the corona. So that's good. This is all common sense that we're seeing. There's a little bit of scatter in the data because every time the Parker Solar Probe arrives at about the same place, the density that you find there changes by a little bit each time. And that's what we call natural variance of a parameter. If you go into a classroom and measure the height of your students, there's a variation that you will find there. And if you go into different classrooms, you'll find a different variation. So you'll get, students are 5 feet tall, but the variation can be plus or minus 3 or 4 inches, depending on where they are in their growth, process. So every physical parameter that we measure is like that. You've got an average number that's close to the mean in a distribution, and then you have a kind of a variation about that that depends on when you measured it and the circumstances of your measurement. Well, anyway, okay, if we use Excel spreadsheets trend lines and we put in a power law, nature loves power laws, absolutely loves them. You find power laws everywhere. And what power laws are is basically it's a number raised to an exponent and multiplied by another number. And so you basically have a 2-parameter function of A and N. N is the index of the power law, and A is the scaling coefficient. And so we want to find a power law that matches this data as well as possible. So we're going to experiment with different values for A and different values for the index. And they're illustrated by the curves that I have there. You'll find that as we get out towards the outskirts beyond 15 million kilometers, all 3 possibilities, index of 1 over x squared, 1 over x to the 2.5, and 1 over x to the 3.0, they all seem to lead to roughly the same kind of variation that, does a fair job of matching the data. It's only when you get within 15 million kilometers of the sun that these predictions change. They vary rather dramatically from what we actually measure. That can mean any number of things. It can mean that there is new physics that exists inwards of 15 million kilometers that isn't well represented in our simple power law function. That's sort of a fair way of looking at it. But what we're trying to do here as sort of our objective is we're not trying to come up with a new theory for the mass distribution of the sun beyond its surface in the corona. We're just trying to come up with an educated guess as to what kind of a density the Parker Solar Probe is likely to experience when it gets within 7.3 million kilometers of the sun. Unfortunately, if you look at where that point lies, 7.3 lies, right in that area where these 3 functions tend to diverge rather dramatically. So that's not a good sign. That means that our prediction, if we use these curves, is likely to show a lot of variation that we're going to try to improve to make a better prediction. But since this prediction that we're making is not based on physics, we're not putting a physical theory to a test here. We're just taking some data and putting a trend line through it and using the trend line in a naive way to predict what the next data point is going to look like. So there's no hidden physics here that we're going to talk about. So anyway, we can look at one of these, the choice of n equals 2.5, which means that the density varies as 1 divided by the distance to the power 2.5. Okay, so that means that it's going to blow up as you get closer and closer to the sun, because we're looking at something that's 1 over d to the 2.5, and as you make d small, the number is going to become exponentially larger the closer you get to the sun. But right now, the numbers that seem to match, sort of more or less, in our first trial, would be this one, which is the red curve. The red curve seems to make the best match to the outer portions beyond 15 million kilometers. It does a crappy job inwards of 15 million kilometers, but in this particular case, we can't really have both at the same time. But let's try to do something else here. The one that I've selected, call it A2, I'm going to adjust the A2 coefficient until I get a better match. The trend line that was given by Excel gave, if we go back to the previous one, it gave A as 871,400 for an index of 2.5, and that gave you that red curve, which was kind of wonky. But if we change that A to 600,000, that curve slides in a bit more in the closer distances. It actually matches the data, not too poorly. It's the better curve that we could come up with by just changing the A coefficient for that particular power law. And essentially, this is as good as we can do, without going into detailed physics and coming up with compound curves. I mean, one possibility is to use one power law for the densities beyond 15 million kilometers, and to use a second power law for the distances less than 15 million kilometers. But now we have two different power laws, and we don't really have enough points to really nail down what the A coefficient should be or what the index should be with so few points at each distance. So we're going to just use the one curve, and basically it's going to be our best shot. So, okay, what we're going to do is use that curve, and now we're going to ask the question, well, what do we think the Parker Solar Probe should see at a distance of 7.4 million kilometers? We're going to use that prediction curve to set what that number is, and it comes out to about 4,000 protons per cubic centimeter, and that's the point that the arrow, the black line, is pointing to. If you look, meanwhile, at the other points along the curve, they don't do such a bad job of matching the densities that we find at these different distances either. Keeping in mind that each one of those dots probably has an uncertainty associated with it that could be as much as a factor of 50%. So that point that's at 1,000 protons per cubic centimeter could be 1,500, or it could be as small as 500. So you can see that point could wobble up and down relative to that red trend line curve. So in retrospect, this isn't such a bad model. We've eliminated the other models with an index of 2 or 3 because they really did a poor job of fitting the distant tail and doing the interior part as well. So this is sort of our best guess as what we might expect to see for the density profile of the sun. And so our prediction is that Parker, when it gets to perihelion on December 25th, when it makes its proton measurement, it should see maybe about 4,000 protons per cubic centimeter. Again, that number could be dicey by a factor of perhaps 50%, depending on the exact circumstances of the corona at that moment in time. So, this is a good guess. I'm really happy with it, and I'm looking forward to seeing what the actual value is. Once I find out what that value is, I'm going to update this plot with the actual value, and we're going to see just how good this guess was. But anyway, let's do something else. Let's pose this question to ChatGPT. For these 14 episodes, each time I go through one of these advanced things, or even the intermediate, I say, well, let's pose the question to ChatGPT and see what it says. So I pose the question, find a power law of the form y equals ax to the minus 2.5 that fits the 6 data points, and I gave it the 6 data points in xy form. Find the best value for a that passes close to the 3 points. Show your work. And so here's what it gave me. In the right-hand column, I told it to show your work, and this is what it gave me. And it came up with an average value of 1.5 million. Well, if we put ChatGPT's prediction of 1.5 million on this curve as the average value for A that would work, it gets that black curve up there, which you can see by eye doesn't match the data at all. In fact, our red curve matches the data far, far better with a value of 600,000. So this goes to show you that ChatGPT provides the worst fit of all trials because it does a simple-minded straight average of all 6 values for A, all right? And that's not the way to work with power law fitting. It just simply doesn't work that way because these are power laws that you're working with. And so the coefficients that you're averaging together are not going to be uniformly weighted. So anyway, this is what ChatGPT gives you. I'm still very proud of our red curve, not a bad guesstimate. And again, there's no physics in this. This is just doing a trend on some data points. It's interesting that if you were to do other kinds of experiments, like, for instance, taking a ball, plotting its height and its speed at different heights, I mean, you should normally get the acceleration profile that's provided by Earth's gravity, or a uniform gravity. But in fact, if you gave this to ChatGPT, it might come up with, instead of an inverse square law for the force of gravity, it might come up with an inverse 1.3 law or an inverse 2.8 law or some other kind of nonsensical kind of a thing. So that's why you have to be careful using ChatGPT. Even under these very controlled conditions that you think are controlled, ChatGPT is going to go off into its own universe, and we don't know what it does. We don't know how it thinks, but it comes up with answers, even mathematical answers, that you always have to double check. And for this, the easiest way for us to double check ChatGPT was to simply plot its answer. Okay, well, that's all I have this time. I'm waiting with bated breath to see what the actual density value is going to be at perihelion. And I hope this episode has shown you a number of different things about using mathematics to probe various aspects of the sun. We did a simple calculation of the rate at which the sun is losing mass. We also compared that to the amount of mass of the sun, and discovered that it was an insignificant amount. That's a major accomplishment when you actually sit back and think about it. We deduced something very important about the evolution of the sun just using the properties of a spherical shell with a thickness, with a small thickness, and calculating from mass equals density times volume, what the mass was within a second, and so forth and so on. And then we have this advanced sort of approach, which involves taking data points and doing a trend line fitting, optimizing the trend line so that it better matches the points, and then comparing that against ChatGPT to get what we hope is a much better prediction. And so if you have any questions, just as a teaser, next time in January, we're going to answer the question, is the Earth about to reverse its polarity? We're going to go over facts and misconceptions. And one of the biggest misconceptions is that the Earth's magnetic field does not look like this at all. It's not produced by a bar magnet in its core or anywhere else in that way. And we'll discuss that misconception, which is rampant in all the artistry that's done about the Earth's magnetic field. So, all right, with that said, I am going to stop sharing and return to our program. Okay, and I am going to entertain questions.
Thank you, Stan.
Hopefully with a little levity.
Yeah, if anyone has any questions, feel free to unmute yourself and ask away. There were a couple things in the chat. Someone mentioned that AI will not calculate air resistance. Seems kind of a big miss there.
If you go back and look at some of my previous challenges to ChatGPT, one of my most amusing challenges was doing the student's t-test on some data to see if it was correlated with a function. And what it kept doing is I gave it 50 points. And part of that is that you have to calculate what the average, the X and Y averages are for your points. It would keep insisting that instead of 50 points, there were only 45 points. And so it would give me the wrong average. It would give me the wrong t-test. And instead of saying that there was no correlation, it would say, yes, there is a correlation between the number of sunspots and the number of songs published each year about the sun. So, anyway, that was just one. It did acquit itself on a couple of other problems. So it's very, very non-uniform in the way it performs. Anyway, so.
I have a question from Matthew.
Hey, Dr. Stan,
Hey
have
there.
you heard about the 3.8 challenge from the social medias of Facebook and X?
No, not familiar with that.
It says from December 17th to Christmas Eve. And have you heard that?
No, I haven't heard that either. I'm sorry. This is new territory for me.
It's a fun riddle, and all the mathematics and all sorts of trivia problems and handy. And this time, you should be able to figure out your answers on your own.
Well, I am very proficient with Facebook. I do not subscribe to X because I do not like Elon Musk. And I wasn't even a Twitter person for various other reasons. So basically, I'm listening to your question with one hand behind my back.
Thank you.
Okay, sorry about that.
We have another question from Soleil.
Thank you so much for pronouncing my name correctly. Can you hear me?
Yes,
Yeah.
thank you.
Thank you. I actually had two questions, if that's okay. Granted, all of my research is self-done, so forgive me if I've got bad info. You said the Parker Solar Probe is not entering the corona?
Yes, it is.
Okay. That's what I thought.
It's not entering the corona that you can see with the naked eye during totality. It's just a little bit outside of that, but that depends on how you photograph it, in fact. But no, it's definitely in the corona. It's pretty deep into it, in fact.
Yeah, that was my understanding, because they found, right, like you showed on the presentation, the often critical surface, which I thought was kind of, where the corona, quote unquote, starts, even though it's not a straight sphere,
Right. Yeah, it's an interesting thing. At a distance of about 2.5 solar radii, you get to the outskirts of the visible corona, which is produced by Thomson scattering, and you're actually entering the domain of the zodiacal dust corona, which extends from there all the way out into interplanetary space. So it's an interesting place where we think a lot of interesting things go on in a variety of components for the corona.
Yeah, that sounds very fascinating. So my second question, I guess, is a very good lead in from what you said, which is, could you tell us a little bit more about switchbacks, how they're caused from the supergranules? I kind of missed that slide a little bit.
My gosh, it would take me a while to do this, but all right, in simple terms, you have one kind of magnetic field that comes out of coronal holes. All right, these are outgoing magnetic fields, very large loops. And so you can think of that as one kind of a surface that goes out into interplanetary space. It's also kind of a magnetic pipe that lets particles from the inner corona and the photosphere stream out almost uninhibited, and this forms what's called a high-speed wind stream. Now, the particles involved in that have a certain chemistry. They have a certain abundance of specific elements like iron, oxygen, hydrogen, nitrogen, things like that. So for coronal holes, they have one specific kind of fingerprint, all right, chemically. On the other side of the coronal hole, you have magnetic fields that come from the transition region and the outer corona, and these are things that are often associated with the boundaries of granule cells. And at the boundaries of granule cells, you have magnetic fields being compressed, being stretched out. You have matter being loaded onto those magnetic fields. And those form sort of like the other side of that wall with the coronal hole and the high-speed wind stream. Well, what turns out is that those particles also have a specific kind of signature. They tend to be more abundant with hydrogen atoms, protons, and other elements. And so you can compare the element abundances on each side of a coronal hole, and you can actually earmark where that plasma is coming from, whether it's coming from the surface or from the corona. Now, switchbacks are areas in the corona where you see magnetic field lines change their topology. And as they do that, Parker has been able to measure that there is a composition that's associated with that that's related to not the coronal hole plasma, but the plasma on the other side, which is far more abundant and far more dense. So these switchback regions are associated probably with the source of the matter that dominates the solar wind, because the coronal holes, that is a high-speed wind stream of fairly low density, and it's not associated with the solar wind itself. So by using compositional differences and looking at the geometry of these switchbacks, you could actually piece together that the origin of the solar wind seems to be from events happening at the granule boundaries. And there are things that we know that occur at the boundaries of these granules, things like microflares and nanoflares. And if you see them sideways on the sun, they actually look like plumes and jets of gas leaving the surface of the sun. So we now have a kind of a holistic picture of where the solar wind comes from. It comes from the boundaries of these granules where there is mass outflow in these nanojets, and the magnetic field funnels this into the upper corona, and you can measure the composition of these particles, and they trace all the way back to the photosphere in composition. So it's a picture that now is starting to hang together pretty nicely. That's a long-winded explanation for.
No, thank you very much. That was fascinating. Thank you.
And I think about 70% of what I just said is currently correct. But, you know, as we're learning more, there are exceptions to rules and things like that that we're discovering. Anyway.
Sure, and that's science, you know?
In fact, the November issue of Astronomy magazine, I wrote an article about the 10 biggest discoveries in polar physics this year. And one of those is exactly this subject. So for further information, you should read my more coherent explanation in the magazine.
Absolutely. Which magazine was that again?
Astronomy.
Thank you.
Sten, this is Gerald. I have two trivial questions. You might have maybe answered
I'm
the
sorry,
second.
Gerald. We don't do trivial questions in these webinars.
Okay.
You need
It's
to
not-
upgrade.
Yeah. Well, I'm in any case, I'm not sure if you answered the second already or not, but just let me know. The first one is, what happens to Parker Solar Probe after this orbit? I was fascinated with your animation, and I was thinking, okay, what's going to happen when it circles around again and again and again? Is it going to keep doing this forever, or
Oh
what?
yeah, it'll do it about another 10 times before NASA has to reinitialize the funding for continued data analysis. That generally is tends to be automatic for very successful spacecraft.
And
So it's
will it
going to
keep-
probably do 50 or 60 orbits by the time it's basically overheated or whatever.
And that's related to question number 2.
Mhm.
I assume, will it keep getting closer or just bottom out at where it is
Well,
on this one?
That's a very interesting question. The astrodynamicists, they haven't published a public sort of image of future trajectories because they don't know if they're going to be funded. But I'm sure that's going to be part of the proposal for continued funding, is that they're going to show, you know, the next 30 orbits. And there probably will be orbits that'll be even closer. You see, the problem is that, you know, the orbits are determined by interactions with Mercury and Venus as well, gravitational interactions with these two planets. And so it's complicated. They're not going to look as nice and pristine as what you see here, because they weren't designed to have nice looking orbits for the far future, only for the 30 missions, 30 perihelia that it was initially funded for.
Yeah, I understand. Well, and so the follow-up question, you know, if an airplane flies through a tornado, sometimes it's in trouble. And I wondered what would happen if Parker Solar Probe flew through a CME, a strong one. Would it just do nothing, or would it blow it away?
That's a really, really good question. I have absolutely no answer to that. All I can think of is that at the distance of the Parker probe and at the density contrast that you typically see for CMEs, it probably would register maybe a factor of 10 increase or 50 increase in the density. But I don't think that's going to be sufficient to do much, you know, to the probe in terms of its orbit. It might knock out some of its detectors, which probably have a saturation level. But I suspect, given that the probe was sent to the sun, the saturation level for detecting the density of particles was probably set pretty high, because they didn't really know to within a factor of 10 what the actual densities would be. So there's probably some margin there, and it'll probably be okay for some of the weaker CMEs, but for really big ones like a, you know, Carrington event, or like the Halloween 2003 events, you know, it's who knows what'll happen to it.
Yeah, well, thank you. This is another one of your fascinating presentations. I wish you had been my math teacher when I was younger. I had a pretty good one, but your stuff is even better. Thank you.
Thank you. Thank you very much, Cheryl.
So kind of piggybacking on that, there's another question in the chat. In the previous session, we learned about solar radiation. What effect does that have on the Parker Solar Probe?
There are two forms. There's sort of the visible light radiation, which basically heats up the probe. And we think we have that under control with this very big heat shield. Radiation damage from solar proton events and things like that, that's much more problematic. I don't know firsthand how radiation hardened the Parker Solar Probe is, because statistically, every time it reached perihelion, I think the dice game was that there's not likely to be a major radiation event occurring exactly at that time when the Parker probe is the most vulnerable. But it must have some modicum of radiation shielding. The way you do that with electronics is that instead of using, you know, nanoscale traces on your integrated circuits, you make them a micron wide, so they're much more radiation hardened. I'm sure they used radiation hardened electronics, which means that, you know, we're not talking about, you know, gigahertz speed processors. We're probably talking, you know, megahertz speed processors. So it's slower computation and things like that. So, you know, I suspect they did the best they could, and it's probably okay for most kinds of radiation effects.
And another question from Soleil.
So you said that the length of the Parker Solar Probe mission depends on funding, and if it gets renewed. I had also read that there's a finite amount of fuel for the probe to adjust as it rotates the sun.
Yes. Yeah, there are expendables, and once they're gone, they're gone.
Right. So even if we get funding, you know, we're not going to be able to get that fuel back. So what happens then?
Right. Yeah, it's I have to apologize. I didn't really burrow that deeply into the Parker Solar Probe, you know, guide for scientists to be able to tell you whether or not the 35 orbit limit is set by the exhaustion of the expendables and the steering gases, or if it's just basically a hard funding limit. You might be right. It might have to do more with the availability of these expendables. That would be the natural number that a planner would use in determining how many orbits would be necessary to model.
Yeah,
Gotcha.
great. Are there any more? Sorry. Great questions. Thank you, Sten. Are there any other questions? We have hit the top of the hour. Great questions and another great presentation. We're going to be really excited on Christmas Eve or Christmas Day when we have this fun perihelion.
Don't forget, January, we have, is the Earth about to go into a magnetic reversal? And what's going to happen when it does? That's going to be the big question.
And that's the question that a lot of kids have, I've found too. So that's going to be, I'm looking forward to that one.
Yep. Okay. Well, thank you all
Thank you,
for
everyone.
attending. See you next time.
Take care.
Thank you.
Bye-bye. Thank you.
Bye.